Okay, I think we can get started. Hello, everyone. Together with my IAA colleagues shown here, I'm delighted to welcome you to this inaugural talk of the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we'll have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Professor Jeannette Wing. Dr. Wing is Avanesian's Director of the Data Science Institute and Professor of Computer Science at Columbia University. She is Adjunct Professor of Computer Science at Carnegie Mellon University, where she twice served as head of the Computer Science Department and had been on faculty since 1985. From 2013 to 2017, she was Corporate Vice President of Microsoft Research. Previously, she was the Assistant Director of the Computer and Information Science and Engineering Directorate at the National Science Foundation. She received her undergraduate and PhD degrees in computer science from the Massachusetts Institute of Technology. She has received numerous awards and distinctions from scientific boards and associations, and has been recognized as a Fellow of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, the Association of Computing Machinery, and the Institute of Electrical and Electronic Engineers. Professor Wing's general research interests are in the areas of trustworthy computing, specification and verification, concurrent and distributed systems, programming language, and software engineering. Today, Jeannette will talk about one of her recent research directions, Trustworthy AI. Jeannette, we are excited to have you kick off the fall seminar series. Welcome.
Thank you very much. I'm going to share my screen. So I am delighted to be able to have this opportunity to talk about a new research direction that I'm trying to encourage the entire computing and beyond community to pursue. I am especially talking to the graduate students in the audience who are people who are looking for thesis topics because there's a lot of questions I'm going to raise and not many answers. So let me start by, first of all, acknowledging my supporters, the Columbia University Data Science Institute, the Sloan Foundation, and the National Science Foundation for helping me kick off this new research direction, which I call Trustworthy AI. And I think it's quite appropriate for me to talk about Trustworthy AI to the Institute for Assured Autonomy. So, of course, we understand the astonishing success that AI has achieved, matching or exceeding human performance. We already have vision systems in self-driving cars or semi-autonomous vehicles that help us in real time recognize objects, make sure that we don't hit pedestrians. We have AI in our homes with speech recognition and speech understanding. And of course, AI has beaten the best Go player, human Go player in the world. So this is quite astonishing. I have witnessed the rise of AI in the past 5 to 7 years. And we, it really is something to acknowledge. And now, of course, every sector recognizes that they need AI in whatever they do. So this is quite a positive direction for the research community in AI. We also argue, and I think rightly so, that AI can benefit humanity and society. I already mentioned self-driving cars. The whole idea of having autonomous vehicles or self-driving vehicles is that we can avoid traffic accidents on the highways and in our roadways. thus saving lives. We are seeing a lot of excitement of the use of AI in medicine, especially obviously in imaging, where in this particular example, I am showing that AI technology was able to detect or classify whether something was cancerous or not, outperforming a suite of neuroradiologists. We know that AI is already being used in the criminal court system. This is to try to assure that the decisions are fair and not made based on the diversity of human judgment. We also know that AI is being used in more routine human resource activities like hiring. Sometimes you go through a very long hiring process in a corporation and you don't speak to a human being until the very end because of all the filtering that happens through AI technology. So AI has the promise of truly benefiting humanity and society, and I think we as scientists and technologists really want to see that come to fruition. There's the but. Why should we trust AI systems, AI-based systems? And here are the perils of AI, if you will. We know very easily how to fool classifiers. Just by putting some graffiti on a stop sign, we can change the classifier to say it's not a stop sign, and accidents can actually happen and deaths can occur. Not good. We know how easy it is to add noise to an image to fool the classifier, and in this case, change the classifier into thinking something is benign to something that's malignant. Not good. We also have in mass media, as well as in the academic community, seen many, many articles and scholarly papers published about how these AI decision-making systems actually can be biased. So the whole area of fairness in machine learning, bias, algorithmic bias, and so on, really speaks to the fact that these AI systems can be trained with biased data and therefore make biased decisions. And similarly, in hiring, corporations have been trying to use AI and then recognizing and admitting that some of these automated decision systems can also be biased. So this is quite a conundrum. The question I want to raise is, how then can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In other words, how can we achieve trustworthy AI? So I want to take a step back and explain where I'm coming from. I have been working in the area of what we like to call trustworthy computing since literally the turn of the century, where trustworthiness for trustworthy computing has come to mean a set of properties like reliability, does it do the right thing, safety, does it do no harm, security, how vulnerable is it to attack, privacy, does it protect a person's identity and data, availability, is the system up when I need to access it, and of course usability, can a human use it easily? Where computing, the systems that we think about is hardware, the software that runs on top of it, and of course for properties like usability and privacy, we also include the human users. And in taking this step back, just for historical context, it was actually the Bill Gates Trustworthy Computing memo published first by Microsoft in 2001 that got me interested in this area, because I didn't really know what Microsoft meant by trustworthy computing. And in fact, what I decided to do is to spend a sabbatical at Microsoft Research, in 2002 to 2003, to go on the inside and ask, what does a company mean by trustworthy computing? And at the time, they really talked about 4 pillars of trustworthy computing: reliability, security, privacy, and what they called business integrity. And over time, Microsoft started a trustworthy computing academic advisory board, and I was on it for many years. And I also really got to experience, by being in the inside, what it meant for a large software company to try to make their software more reliable, secure, and so on. And it's no easy feat. Okay, so the other aspect of trustworthy computing I want to acknowledge is the role of federal funding agencies like the National Science Foundation, which also, around the turn of the century, partly sparked by a National Academy's report called Trust in Computing that Fred Schneider edited, NSF started various programs with trust or trustworthy or trust in computing and so on in their titles, starting with the size directorate, one of the divisions within the directorate. By the time I got to NSF, it was directorate-wide. By the time I left NSF, it was foundation-wide, and was with partners in other agencies. So the Secure and Trustworthy Computing program that NSF runs is really speaks to this trustworthy computing effort that's been going on for decades. But I want to push the community further. And this is where I talk about upping the ante from trustworthy computing to trustworthy AI. And I'm going to talk about upping the ante in a couple of ways. In this particular way, we're upping the ante because the properties we care about for AI-based systems are, of course, the same properties we care about for plain old computing systems, all the properties I list on the left, plus more. And that's what I mean by upping the ante. So all of a sudden, we need to start talking about properties like accuracy and robustness and fairness and accountability and transparency and interpretability or explainability and ethics. And properties yet to be defined, because I think we're still figuring out what makes sense to ask of an AI-based system. And let me just walk through very, very briefly what I mean by these properties, similarly as I did for trustworthy computing. So by accuracy, we ask the question, how well does the AI system do on new, unseen data compared to data on which it was trained and tested? On robustness, we ask, how sensitive is the outcome to a change in the input? Fairness is, are the outcomes unbiased? Accountability, who or what is responsible for the outcome? Transparency, is it clear to an external observer how the system's outcome was produced? Interpretability or explainability, can the system's outcome be justified with an explanation that a human can understand and or that is meaningful to the end user? Ethical, was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And so on and so forth. So now let me raise the question that I would like to encourage the entire computing and beyond communities to address. How can we achieve trustworthy AI? And I believe many approaches are needed, just like for our attempt at achieving trustworthy computing requires multiple approaches, and I believe the same will be true for trustworthy AI. However, for the remainder of the talk, I'm going to talk about just one method, just so I can be concrete, and also it is an area that I am familiar with. It's a community I grew up with, and it's also a community that I am trying to encourage to move into new directions to support trustworthy AI, and that is formal methods. So first, let me explain how I want to up the ante for the formal methods community, much like I was upping the ante for the trustworthy computing community. In traditional formal methods, we frame the verification problem with three elements. M satisfies P is how we read that in the red box. M could be a program. It could be a concrete representation of, say, a protocol, whether it's a security protocol, authentication protocol, or concurrent cache coherence protocol, just some protocol. It could be an abstract model of a concurrent or distributed system. In other words, M is an artifact. It's a mathematical object, and it can be, you know, anything as low level as a piece of code to as high level as, say, a state machine. P, let me go to P. P is the description of the property we care about. The property we care about with respect to proving the correctness, let's say, or proving some trustworthy property of M. So P typically is specified in some kind of discrete logic, and for the past few decades, we talk about P as characterizing some kind of correctness property. In the concurrent and distributed systems world, we often characterize these correctness properties into safety and liveness properties. Safety properties are ensure that no bad thing ever happens, and liveness properties ensure that some good thing eventually happens. So we might want to say some distributed or concurrent system is deadlock free. We would characterize that as a safety property, and we might want to say, you know, if I am trying to get cash out of the ATM machine, eventually I get cash out, that would be some kind of liveness property. So the double turnstile stands for a logical framework that allows us to prove that M satisfies P. And double turnstile really depends on, or we read it as satisfies, depends on some mathematical logic and many, many tools that have been built over the decades, and now I'm talking about since the 1980s, for proving the correctness properties of P of some model M. And these tools include model checkers, which have been shown to be incredibly useful, especially for hardware verification, theorem provers, which actually predate the model checking community. And now I think what has really been showing the tremendous success and practicality of formal verification in practice are SMT solvers. So we have a rich history and repertoire of logics and tools at our disposal for proving that some correctness property is satisfied by some program. Okay, from traditional formal now I wanted to mention that sometimes, especially when we want to prove a property about a a concurrent or distributed system, we often include the explicit specification of the system in which the program, let's say, is to operate. And then in a formalism, we might actually use parallel composition to denote how the system and the system environment E interact. So I wanted to just make sure that I included this other formulation of the traditional formal verification framework. Now, what about AI? To verify AI systems, again, I argue we are upping the ante in a couple of very important ways. First of all, there is an analog to M satisfies P in an AI system. So for instance, M for an AI system can stand for the machine learned model. The machine learned model that has to satisfy some kind of property P, like robustness or fairness, or old trustworthy properties from computing like security. And of course, you know, these machine learned models are usually embedded in a larger system, like a self-driving car, where we have maybe a control system, and M is really the larger system that includes the software running on the car and maybe even the control system, and if you really wanted to extend it, the whole cyber physical system. P here, what's new is these properties are likely to be probabilistic or stochastic in nature, and I'm going to speak more about that later. But we are upping the ante in terms of the kinds of logics and tools we're going to need to reason about whether some machine learned model, let's say, satisfies some property like robustness. And so the double turnstile in the task of verifying AI systems can also may also need to use more sophisticated or different logics, probabilistic logics, for example. So we're upping the ante in verifying AI systems from trustworthy computing and formal methods of computing systems, because we all of a sudden really need to deal with probabilistic reasoning, probabilistic models, probabilistic logics, probabilistic properties, et cetera, et cetera. This is something that traditional computing doesn't deal with, because we are so fond of working in the world of discrete logic. Things are on or off, true or false, yes or no, black or white. And all of a sudden we are now talking about systems that output probabilities, systems that have to reason about uncertainty, which can best be represented in terms of probabilities, data distributions that are data distributions, and so on. So another way in which I argue we are upping the ante is some analog, roughly speaking, to specifying the model of the environment, the system's environment, and that is specifying the model of data. So all these machine learned models don't come from nowhere. They come from data that's used to train the models and test the models, so that eventually they can be deployed on unseen data. So there's a specification problem, which is how do we model the data? For example, we could use a stochastic process or just a distribution that generates, but the point is that these data inputs are, we need to model the data if we're going to verify whether the outputs of the machine learned model are satisfy these properties, these trustworthy properties for AI systems. So this is really the way I'm framing the problem. Obviously, expanding on the framing that we have from formal methods, formal verification and specification for regular old computing systems, but now with AI systems in mind. So this is my characterization formally of the problem. And now what I want to walk through is each of the elements of this framing. So let me just remind you how I see the two main differences between traditional verification and verifying AI-based systems. The first is fundamentally a need for probabilistic reasoning, because the artifacts we are talking about are probabilistic in nature. The second is the role of data, collecting and partitioning data, specifying unseen data. That's a specification problem. There's a more technical problem, which I want to get into, which is what we actually quantify over. And then there's the hard task of, well, how do we actually do the verification? And again, I want to remind the audience that I have only questions. I don't really have answers. And this is why I'm really arguing that I'm kickstarting this Trustworthy AI as a new research agenda for the community, and why I'm especially speaking to the graduate students in the audience, and the undergraduates too. Okay, so the need for probabilistic reasoning. M is semantically and structurally different from a typical computer program. M is inherently probabilistic. Internally, think about a deep learning model. M itself operates over probabilities. So just think about how the edges in a DNN are labeled, and outputs results with assigned probabilities. So we might actually be outputting a classification like benign or malignant, but in reality, there's a probability assigned to that classification. Structurally, M is machine generated and unlikely to be human readable. And so this actually opens up an interesting opportunity for the programming language community, because the programming language community is very used to working with intermediate code. But this is quite a different kind of intermediate code. In reality, if you look inside, it's this humongous nesting of if-then-elses. Something, again, a human is unlikely to write. It's something that is unlikely to be human readable, but it is just a piece of code. So it seems to me it's a great opportunity for people who work in static analysis and programming languages to think about how to prove properties about these machine learned models using new techniques. The challenge will be that they operate over probabilities. P may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So for example, robustness properties for DNNs are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. And differential privacy is defined in terms of a difference in probabilities with respect to a small real value. So we can't avoid the inherent domains over which we need to reason and just formulate the problems, let alone the logics. So it seems to me that we have to hit the specification of these properties P head on with the right expression language. And then finally, the satisfies relation showing that say M is correct or M satisfies some trustworthy property, I also believe needs to lean on all the advances that we have made in the past few decades on probabilistic logics and hybrid logics. Fortunately, the formal methods community hasn't been asleep at the wheel at this, because for reasoning about control systems and cyber physical systems and hybrid systems in general, we've had to invent hybrid logics that allow us to reason about both discrete and continuous logic, continuous variables at the same time. We've built probabilistic model checkers, for instance, and so on and so forth. However, I think AI systems, in terms of their scale, would push beyond the limits of what we can do in terms of the tools and the methods. And so we need scalable and possibly new verification techniques that work over reals, nonlinear functions, probability distribution, stochastic processes, and so on. So there's quite a lot of work yet to be done. What about the role of data? D. I want to first distinguish, these are intuitive, informal definitions, between available data, what I call available data, data at hand, used for training and testing, and unseen data. This is the data that we by definition haven't seen before. And the whole idea of building a machine learned model is that we can deploy it in a context and have it operate with some predictability over data we haven't seen before. It will, and it can actually, of course, learn and be updated in seeing new data. So unseen data is data over which M needs to operate without having seen it before. So as I outlined earlier, there are four pieces to describing the research challenges for D, and let me just go through them one by one. The first is the collection and partitioning of data. So we can ask the already asked question, how do we partition an available data set into a training set and a test set? These are obviously questions that the machine learning community has been grappling with and answers in certain ways. But what guarantees can we actually make of this partition with respect to a desired property P in building a model M? And we can even think about the idea of, were we to know that we eventually want to do some kind of verification, would that influence the way in which we do the partitioning? Second, how much data actually suffices to build a model M for a given property P? Does adding more data to train or test M make it more robust, fairer, etc.? Or does it not have an effect with respect to the property P? What new kinds of data need to be collected if a desired property doesn't hold? I'm going to return to this last question shortly, but the idea is, for the most part, when you try to do a proof that some model P satisfies a property P, the proof doesn't go through because there's a bug somewhere. And how do you use that bug to help you resolve either M or P? And in this case, D. Now, what about that problem I mentioned earlier, which is, how do we specify D? How do we specify unseen data? So the general problem is, how do we even specify data or characterize the properties of the data? You know, in the old world of trustworthy computing, we never had to worry about, if you will, specifying much about the inputs to a particular program. At best, we would have a precondition that made some assumptions about the data that is input to a function or a program, and then we be done with it. And included in that precondition would be the type of the data. So we would make sure that the types matched. But I think we need to think much more deeply about specifying and characterizing the properties of the data that we use to train M and to deploy M on unseen data. So we could specify D as a stochastic process. This is a very, it will be a very sensible idea, or simply as a plain old data distribution. If you're in a company and you might actually have historical data that says, here's how the data always looks. It follows this particular distribution modulo some of the actual values for the parameters, then you could specify the data in that way. Elevating the whole discussion to something that I, again, encourage the programming languages community to pursue is using a specification language. And one idea is actually to use a probabilistic programming language like STAN to specify these statistical models. So the STAN is probably the most popular probabilistic programming language. And what is it used for? It's used prevalently by the science community, many people in industry and government, those especially who are trained in statistics. And so they're really, STAN is used to specify these statistical models. Well, can we not use the specification of a statistical model as then a specification of D? And then there's a question of, well, what of large real-world data sets that actually don't fit these common models, statistical models, or which had thousands of parameters? And the reality of the situation is this is the world we're in. Now, there's another problem I wanted to raise in kind of systematically marching through my framework here, and that is breaking the circular reasoning. So to specify unseen data, we need to make certain assumptions about the unseen data. Well, then, would those assumptions not be the same as those would make to build the model M in the first place? I mean, how can we then, the question then boils down to, how can we trust the specification of D? And this seems to be a conundrum in that, how do we break this? How do we get out of this? And there are some practical ways to think about how to get out of this circularity. One is to rely on other techniques, for instance, a repertoire of statistical tools, and I will just enumerate very quickly some of those in a later slide, to break our circular reasoning, to basically give us some confidence in our specification of D. Another is to assume that there's an initial specification of D that is small and simple enough that it can be checked manually by inspection. And then we use the specification to bootstrap an iterative refinement process to build a much more sophisticated specification of D as we try to do the proof, see that there's a problem, refine the specification of D, try to do the proof again, et cetera, et cetera. This technique is actually common practice in the formal methods community. It's called counterexample guided abstraction and refinement. It's shown to be incredibly useful, especially for concurrent distributed systems and especially for large scale systems. So we may be able to borrow from that technique to get us out of the circularity. And then another question is, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? Now, let me turn to a somewhat more technical question, which is also a bit of a quandary to try to answer. The question is, what do we quantify over? In traditional formal methods, we strive to prove a property once and for all x, p of x. So for instance, for all values of the input type for the variable, program variable, we show that some property holds for all those values. And obviously, we might show some, for instance, for all x colon int, p of x, where we show the property holds for all integers, knowing full well that no physical computer can is going to ever, you know, represent or operate over all integers, but we overprove in some sense. But that's the traditional way, and once we do for all x, then we don't have to test individually multiple values of integers. We know it holds for all integers. And similarly, more interestingly, you know, is for a concurrent or distributed system, we want to show for all executions of, say, a state machine, that some property holds. And so then we don't need to test for, you know, one execution over another if we can guarantee that it holds for all executions. And so and similarly, we might say something like for all reachable states for a concurrent or distributed system, we prove P holds, and since you can't reach the unreachable states by definition, then you're assured that the system will satisfy the property, the correctness property. So this is the mentality of the formal methods community for trustworthy computing. But I think for AI systems, we need to adjust our sensibilities. So for AI systems, we do not expect M, the model, machine learned model, to work for all input data, or for all data sets, or for all possible uncertainties in the environment. This is too much to ask for, and it's just not the way we build AI systems in terms of expectation. Right now, we build an AI system. It's actually quite task specific. We deploy it with a particular task in mind. That's not to say we don't take an AI system, build it for one task and plop it in somewhere else. But at least we can say, I didn't build it for that. And so now the question is, what do we quantify over? And so let me try to argue how we might think about this. So how can we specify the class of distributions over which P should hold for a given M? It might be property dependent. So for robustness, for instance, in the adversarial machine learning setting, we might want to show that M is robust to all norm-bounded perturbations D. That is what we're quantifying over. And so we just say for robustness, for this setting, that's what we're quantifying over, and M is robust to that, but I'm not proving or guaranteeing anything else. At least we're being explicit. More interestingly, of course, for robustness, we might want to show M is robust to all, quote, semantic or structural perturbations for the task at hand, because norm-bounded perturbations of D is easy for us to define mathematically, but maybe not relevant for the task at hand. The canonical example being computer vision, where if I have a self-driving car with a computer vision system guiding me down the road, and there is a dent in the car in front of me, I still want the computer vision system to be robust with respect to that dent in the car, saying it is a car as opposed to it's not a car, and do the right thing. So this is the canonical way of saying, you know, we want our machine learning model to be robust, say in this case to certain kinds of perturbations that we would do so that the classifier still says the panda is a panda and not a gibbon. Here's another example. What do we quantify over where it's a different property? So again, the question is, we're not trying to prove for all DD, but we're trying to say for some class of distributions, how could we quantify that class? How could we characterize that class? And so for fairness, it might be something completely different from robustness. This is why I say doing this exercise might be property dependent. So for fairness, we might want to show the machine learning model is fair on a given data set and all unseen data sets that are, quote, similar in some way. So we have a small group of people working on Trustworthy AI at Columbia, and a handful of us were working specifically on the COMPASS data set, which was shown to be, which was used by the criminal court system in the US for risk assessment on recidivism. And what we showed is that if you take a state-of-the-art fair classifier and you train it on this data, and then you very slightly perturb the weights on the data, you can very easily go from a fair classifier to an unfair classifier. And so the fact that you can't basically distinguish between the blue bars and the orange bars is our evidence that for this particular example, it's very easy to go from something that has been deemed as fair to unfair. And so this gives us a way to say it's not going to be easy necessarily to characterize this class of distributions over which some, quote, fair machine learning model will continue to be fair in the future. So let me then finish up the how to specify the D part and look at the verification task of satisfying the model M with respect to a property. How do we check the available data for desired properties? This is where we might want to forget M's and P for a second, knowing, of course, we want to do some kind of verification, and see, can we check D itself as opposed to fooling around with M to see if D inherently has some properties that can be checked. For example, does it even make sense to say, if we want to detect whether a data set is fair or not, what should we be checking of that data set? If we do detect that a property does not hold, then how do we fix the model M, or amend the property P, or decide what new data D to collect for retraining the model? In other words, what is the equivalent of a counterexample in the verification of an ML model, and how do we use it? So as I alluded to earlier, in traditional verification of computing systems, the norm is that what you're trying to prove doesn't hold. You actually find a bug in your program or your system, or the property is too strong. And then you need to fix the program or change the system in some way so that you, or you weaken the property so that you can actually push the verification through. But the output of the verification task, especially if you're using tools like model checkers, gives you a hint as to what the problem is and where to look and how to fix the problem. That's what's called the counterexample. And so now in this world of trying to verify AI systems, and suppose we are able to get this counterexample at the end of trying to push a verification task through, and the answer is no, the property doesn't hold, then what can I do with that counterexample in order to amend M or P or D? The next question is then, how do we exploit the explicit specification of unseen data to aid in the verification task? This is analogous to how do we exploit the explicit specification of the system environment to aid in the verification task for traditional formal methods applied in the trustworthy computing domain. And then how can we extend standard verification techniques to operate over data distributions, perhaps taking advantage of the ways in which we formally specify unseen data? So again, more questions than answers. I wanted to say that there are other opportunities for the formal methods community in this context of verifying AI-based systems. First of all, so far, the AI systems have been quite, as I mentioned, task specific. So can't we then actually take advantage of the fact that we know this AI system is supposed to solve a particular, perform a particular task, be deployed to perform a particular task rather than general AI? The second is something that, again, the formal methods community advocates in some circles, and that is what we call the correct by construction approach, model synthesis, or in the old days we called this program synthesis, where you start with the specification of the property you want of the system, and by systematically transforming that specification, you guide the construction of the end system or the end program. And each step in this transformation is provably correct, so that at the end, you don't have to go back and do post facto verification. The system you end up with has been constructed to be correct to begin with. A lot of the more recent work on program synthesis has been incredibly successful because it's been task specific. Another outstanding problem and approach in the formal methods community is compositionality. So this is where you want to be able to prove some property of some component, and you might do that per component, and you want to know that if you compose all the components, that property still holds. This is, of course, only relevant if your property is called local. It may not hold if it's a global property. The other reason for compositionality, of course, is the only way that we can scale up verification approaches is if we can do the verification tasks kind of on a small component, and then knowing that we can actually compose the result of the verification to scale up. This is one way in which we try to address the scalability issue of verification. And finally, I promised I would mention a repertoire of statistical methods that could really complement the way in which the computing community thinks in general. And of course, the statisticians have been worried about proving properties, or maybe evaluating their statistical models, maybe not so much proving things, but evaluating their statistical models for goodness. And so they use sensitivity analysis, prediction scoring, predictive checking, residual analysis, and something that is come to fore again, an old idea that has really been resurrected, a notion of model criticism. And I think we in computer science can learn from the statistics community and try to understand how these methods might complement more of the verification mentality that we have in computing. Let me just give you one example, concrete example of the potential promise of the idea of robust by construction. And the example is actually quite interesting in that it is inspired by the notion of differential privacy, but in some sense it has got nothing to do with privacy, but the inspiration gives us a technique for giving us a provable guarantee about the robustness of a DNN. And this is a project that has been conducted by my colleague Roxana Gyambasu and her and Daniel Xu, my colleagues, Roxana Gyambasu, Daniel Xu, and Suman Jana here at Columbia, and their students and former students. The idea then is to address this nasty problem of adversarial machine learning, where you can easily perturb the input image like a stop sign and make the classifier produce the wrong answer. And so how do you make this DNN robust to that kind of perturbation with a formal guarantee so that you don't have to test image by image or perturbation by perturbation? And the idea that they use is to insert a layer of noise in the DNN. And this noise is the inspiration from differential privacy. And in this particular case, because you are actually inserting that layer of noise, you can control what that noise looks like and actually which layer you want to put it in. And then by doing that, you can have a provable guarantee that the classifier will be robust to some degree of input perturbations. And so this is the work that they did, and it's in the system they call Pixel DP because it works for images. It's a very nice result, and what it means is that for a range of perturbations, you don't even have to bother proving that the classifier will still say stop sign or panda, and in other words, it will actually output the right classification. Okay, so I'm going to stop here and take questions. This is the summary framing of Trustworthy AI meets formal methods, and thank you very much.
Jeanette, thank you very much for that beautiful talk. When we started this talk, I thought we were on top of the mountain in terms of the promise of AI, and now I realize we're just at the base and there's so much more work to do. So thank you for laying all that out.
Okay, I'm going to stop sharing my screen. Should I, right?
That would be fine. And
okay.
We have a few questions in here. We are pretty much out of time, but you can look at the Q&A as well as I, and there's one that's been highlighted here at the top. At what point do we bring in the non-research human users of any given system to validate any of the technical academic definitions and outcomes of trustworthy AI?
That's a very good question. You know, one could argue that you could bring in the human being, the non-research human users at any point. I think during the process, obviously at the end you need to bring in the human being. But I think we're actually at a point where the academic community doesn't even know how to formalize some of the technical questions to have even the academics, the researchers, to even assess their results, their research results. So we are really at truly the beginning of what I am trying to argue is a long-term research agenda. But I think we can learn from the past in that it is important to bring the non-research human user in as soon as it makes sense, because in the end, we are going to want these non-research human beings to use the tools we invent and use the logics and the languages that we design. And if they're impenetrable, then no one's going to use them, no matter how beautiful the math is.
Because they won't trust them, right?
Exactly.
So I think it's pretty much all I could do from the Q&A list, but I wanted to offer, if any of the people on the panel have a question they want to ask Jeannette, we could do that as a final question.
Jeannette, this is Tony DeBora. Hi.
Hi, Tony.
You alluded to this several times during your talk, but maybe not explicitly. I come from the old school communications protocol conformance testing world. And so there's a traditional notion of state. And maybe can you address how the concept of state applies in this so-called new world of machine learning based systems?
It's a good question. I think this kind of reminds me of decades ago when we would talk about what is the right way to think about a concurrent or distributed system. Is it a sequence, is a behavior of a concurrent system a sequence of states, or a sequence of events, or a sequence of states and events? And what is actually in a state, and what is observable, because that's what matters, what's observable. And we would get ourselves into these, you know, debates, and people would go off and formalize behaviors of concurrent systems in terms of one or the other, or both, and so on and so forth. Now, for AI systems, first of all, there are still those questions. But I think also is what is in a state, what do we represent in a state, is also relevant. You know, in more traditional programmatic, you know, computing systems way, a state is a set of variables, each of which has a value, and you can think of a state as just a mapping from variables to values. But in our world of AI systems, do we think about variables, program variables that maybe map over probabilities, or sampling over some probability distribution? You know, Tony, you go like that, and I go like that too, because I don't think, you know, not until we ask these questions do we then realize there are many possible answers. Or ways, let's say there's probably no right answer, but there are many possible ways to think about it, and taking any one such way to think about it might lead us to make progress. So I would say we're really at the beginning of this, you know, so I can say
agree.
more,
Thank
but
you.
You get the point.
Thank you.
Thank you. Thank you to Jeannette for giving a wonderful talk. Thank you to the participants and the panelists. And we look forward to many more exciting outcomes from this new line of research.
Thank you very much for this opportunity. I really appreciate it.
Have a good day.
Bye-bye.